Welcome back again, guys. Alright, so finding the limit of a trig function works the exact same as finding the limit of any other function. To evaluate a limit, the first thing we do is substitute, and if substitution works, then cool. So find the limit of this function here. I'm going to go ahead and substitute. I get secant of pi over 6. Pi over 6 is the same as 30. Secant of 30, if you want to look at a triangle, we've got a 1, 2, square root of 3. Secant is so I have 2 over rad 3. I rationalize and I get 2 rad 3 over 3. This limit does in fact equal 2 rad 3 over 3. Let's try another problem. Give it a shot, see what you get. Alright, I'm going to substitute 3 pi over 2 for x. 3 pi over 2 is the same as 270. Looking at a curve, sine 270 is negative 1. Negative 1 plus 1 is 0. 0 is the answer to this limit. So finding the limit of a trig function can be just as straightforward as finding the limit of any other function. But also, just like the other functions, finding the limit of a trig function can get more complicated. Look at this problem here. And just like we've said before, to evaluate a limit, the first thing we do is substitute. So we're going to go ahead and plug in 0. When we do, we get sine of 0 over 5 times 0. That's 0 over 0. That's indeterminate. And we know an indeterminate limit means 3 things. It means there is a limit, I must manipulate the function to find it, there's a removable discontinuity, and to deal with a 0 over 0 indeterminate limit, we can try to factor, we can try to polynomial divide, we can try rationalizing by the conjugate, and if that doesn't work, we can just do what the math is asking us to do. But none of those really seem to apply to this problem. So that leads us to the last thing on our limit chart on the left-hand side. Take out your limit chart. And as we work our way down the limit chart, all the way on the left-hand side, our fifth and final option is to look for the limit trig combos. Now there are sort of 2, sort of 4 combinations, but we're going to start with 1. We're going to start with the limit as x goes to 0 of sine x over x. This is the function y equals sine x over x. And as we zoom in, you get a really good picture of what's happening as x approaches 0. Let's take a closer look at this function. If I approach the x value of 0 from the left-hand side, what y value am I approaching? I'm approaching the y value of 1. And if I approach the x value of 0 from the right-hand side, what y value am I approaching? Again, I'm approaching 1. The limit of sine x over x as x approaches 0 is 1. Let's write that on our limit chart. We just saw that the limit as x goes to 0 of sine x over x equals 1. Now it's just an idea, it's just a thought, but what happens if we flip this function over? What is the limit as x goes to 0 of x over sine x? Let's go see. You can still see the original function y equals sine x over x in blue. Now I've added the new function y equals x over sine x in red. They're very, very different functions, but let's take a closer look. You can see that even though these functions are very different, as this new function approaches 0 from both the left and the right, we still get a y value of 1. The limit for both of these functions is 1. So back on our limit chart, I'm going to make a note that the limit as x goes to 0 of x over sine x is also 1. It helps me to remember that if I have equivalent expressions on both the top and bottom of a fraction, I'm going to get 1. And then if I flip that fraction, so I still have equivalent expressions on both the top and bottom of the fraction, I'm still going to get 1. You can flip a fraction that equals 1, and you still have equivalent expressions top and bottom. It's still going to equal 1. I need to show you one more set of limit trig combos. There's another set that we need to know, and they come from the function y equals 1 minus cosine x over x. We need to find the limit as x goes to 0 of 1 minus cosine x over x. So let's take a look at that function. Here you see the function y equals 1 minus cosine x over x. Let's zoom in a bit. Let's take a look at the y value that we're approaching as we approach 0 from both sides. From the left, our y value is 0. From the right, our y value is 0. The limit of this function is 0. So back on our limit chart, I'm going to write that the limit as x goes to 0 of 1 minus cosine x over x equals 0. And the natural question might be, well, can this fraction flip also? Does that work? Well, think about it. If you have a fraction that equals 0, say 0 over 2 plus 3, that's 0 over 5, that equals 0. Can you flip that fraction and still get 0? 3 plus 2 over 0 equals 5 over 0 equals undefined. No, I definitely can't flip the fraction vertically. But what can I do with it? Well, consider this idea. If we had, say, 5 minus 3 plus 2 over 7, that would give me 0 over 7, which equals 0. We know we can't flip it vertically, but what if we flip it horizontally? And by that, I just mean flipping these two terms, like this, 3 plus 2 minus 5 over 7. That still gives us 0 over 7, which equals 0. The cosine limit trig combo doesn't flip vertically. Instead, it flips horizontally. We need to go look at the limit as x goes to 0 of cosine x minus 1 over x. I've now brought in the function y equals cosine x minus 1 over x. I have it in purple there. You can still see the original function in green. Let's go ahead and zoom in. And as you can see, this new function also approaches a y value of 0 as we approach an x value of 0. The limit of this function is 0 also. So I'm going to add that to my limit chart. The limit as x goes to 0 of cosine x minus 1 over x equals 0. And this is why I said there were kind of 2, kind of 4 limit trig combos. If you can remember the original, you just need to remember that the sine combo flips vertically. And if you can remember the original cosine combo, you just need to remember that the cosine combo flips horizontally. Notice too that each of these limits is approaching 0. If they were not approaching 0, the limits of each of these functions wouldn't necessarily be the same. These combinations are really important, and they're going to come up a fair bit in calculus, so you need to remember these. The limit as x goes to 0 of sine x over x equals 1. Pause the video and say that to yourself over and over until you have it. The limit as x goes to 0 of sine x over x equals 1. The same thing with the other one. The limit as x goes to 0 of 1 minus cosine x over x equals 0. Pause the video, say that a bunch of times until you have it. The limit as x goes to 0 of 1 minus cosine x over x equals 0. And again, remember, the sine combination flips vertically, the cosine combination flips horizontally. Now, having said all that, let's go back to the problem that we started with. Here we are. We plugged in 0, we got 0 over 0. None of the other ideas on our limit chart are going to work for us. So we're going all the way down to the final possibility using the limit trig combos. This is clearly going to be the limit trig combo that deals with sine. And do you remember what the limit trig combo that deals with sine is? It's the limit as x goes to 0 of sine x over x. And what did it equal? It equaled 1. So that's the combination that we're looking for. But that's not what we have. Looking at this problem again, I have the limit as x goes to 0 of sine x over 5x. And I can see the sine x over x combination that I'm looking for right there. But I have a 5 on the bottom, and that 5 is not part of my limit combo. So what can I do with that 5? Well, that 5 is part of a fraction. It's actually a 1/5. And if you remember, constants can pull out of the limits. So I can pull out this 1/5, and I have 1/5 times the limit as x goes to 0 of sine x over x. This limit part, the limit as x goes to 0 of sine x over x, is simply going to equal 1. So I now have 1/5 times 1. My answer is 1/5. There's still a restriction where x can't be 0, and there's a removable discontinuity at 0, 1/5. Try this problem, see what you can come up with. To evaluate a limit, the first thing I do is substitute, and if substitution works, then cool. But I can see pretty quickly that if I plug in 0, I have 3 times 0 over sine 0. That gives me 0 over 0. It's an indeterminate limit, and I know that none of the other 4 options are going to work for me. I'm going straight to that limit-trig combo. Do you remember what the limit-trig combo is? Well, the one that most resembles what I see in this problem is the limit as x goes to 0, x over sine x. And what did it equal? 1. So starting again, I can see the combo that I'm looking for right there, and I can pull the constant out of the limit. This entire limit part just equals 1 because of the limit-trig combo. So I now have 3 times 1, which is just 3. I have a restriction that x can't be 0, and there's a removable discontinuity at 0, 3. Let's look at one more kind of like this. To evaluate a limit, the first thing I do is substitute, and in this case I get sine 4 times 0 over 0, which gives me sine of 0, which is 0 over 0. Again, I'm dealing with a limit-trig combo, but the big mistake that people make with this particular problem is they just grab the 4 and they pull the 4 out of the trig function. That is not allowed. You can't just pull numbers out of the argument of a trig function. Think back to when we were dealing with trig functions and we derived sine 2a. We couldn't just pull the 2 out. It didn't equal 2 sine a. That wasn't allowed. Constants don't pull out of trig functions. So how do we deal with that 4? Going back to our limit chart, looking at the limit combinations, it's important to understand that each of the variable terms match exactly. Again, each of the variable terms, x and x, match exactly. If I were to sketch sine 4x over 4x, the picture would be different than the picture we looked at for sine x over x, but the limit as x approaches 0 would still equal 1. So just remember, each of these variable terms must match exactly. So coming back to this problem, the limit property that this most resembles is the limit as x goes to 0 of sine x over x, which we know equals 1. But we also know that these terms must match exactly. And at this point, they don't match exactly. I'm missing a 4 on the bottom. So what can I do? How can I get a 4 on the bottom? Well, I can multiply a 4 on the bottom. But what I do to the bottom, I have to do to the top. 4 over 4 is just a fancy version of 1. So multiplying that in, I get the limit as x goes to 0 of 4 sine 4x over 4x. Now my variable terms match exactly, and I can see the limit combo that I'm looking for right there. I can pull my constant out of the limit, and I have 4 times the limit as x goes to 0 of sine 4x over 4x. That limit combo simply equals 1, and I get 4 times 1, which is 4. That's the limit. My restriction is that x can't be 0, and there's a removable discontinuity at 0, 4. Now sometimes people look back at this problem where it started, and they say, yeah, but isn't it the same if we just pull that 4 completely out and we get 4 times the limit of sine x over x as x approaches 0 and then use the combination? That equals 1 and we end up with 4. Isn't it the exact same thing? And yeah, it is the exact same thing. Oftentimes that's how it works out. Except that's not the math that's happening. This math that I did down here, that's illegal mathematics. You can't do it that way. And while the answer might end up the same, that is not the math that's happening in the problem. Let's try another one. Give it a shot, come back when you're ready. Alright, plugging in 0 does give me 0 over 0, so I know it's indeterminate, and I'm looking at a limit-trig combo. The limit-trig combo that most resembles this is the limit as x goes to 0 of sine x over x, which equals 1, and I know that these two have to match exactly. Now be careful when doing these. It's easy to look back and say, okay, the bottom's 5x, I need the argument of the sine to also be 5x, but that's not true. The 5 on the bottom isn't really a problem. I can see the limit-trig combo that I'm wanting right there. I can treat 3/5 just like a coefficient or a constant and pull it out of the limit completely. Now you see the limit-trig combo, which just equals 1. 3/5 times 1 equals 3/5. There's a restriction that x can't be 0, and there's a removable discontinuity at 0, 3/5. How about this problem, guys? We've got the limit as x goes to 0 of 9 minus 9 cosine 2x over 3x. This one's going to be a fair bit more complicated. Alright, so when I plug in 0, I get 9 minus 9 cosine 2 times 0 all over 3 times 0. That's going to be 9 minus 9 cosine 0 over 0. Cosine of 0 is 1, so what we have is 9 minus 9 over 0. We have 0 over 0. I know I'm using the limit-trig combo for this problem, and the limit-trig combo that most closely resembles this is the limit as x goes to 0 of 1 minus cosine x over x, which equals 0. But this problem is quite a bit different from that combo that I'm looking for. So let's start fresh. First, let's deal with the 9s. We can factor out the 9 to give us 9 times 1 minus cosine 2x over 3x. From there, we can treat the 9 over 3 like a coefficient or a constant and pull it out of the limit. We can reduce it at the same time, so 9 divided by 3 is 3. We now have 3 times the limit as x goes to 0 of 1 minus cosine 2x over x. We're much closer to the limit combo that we need, but we know that these variable terms must match exactly, and right now we have a 2x on the cosine, so we need a matching 2x on the bottom. What we do to the bottom, we also have to do to the top, so let's multiply the top and bottom by 2. That gives us 3 times the limit as x goes to 0 of 2 times 1 minus cosine 2x over 2x. I can see the combo that I'm looking for right there. I can again pull this constant out of the limit, multiply it times the 3 that's already there. So 3 times 2 is 6, and then I have the limit as x goes to 0 of 1 minus cosine 2x over 2x. This combo that I see equals 0. So what I have after all of this is 6 times 0, which equals 0, where x can't be 0, and there's a removable discontinuity at 0, 0. For the problems that involve the cosine limit-trig combination, most often your answer is just going to end up being 0, because when you multiply anything times 0, you're going to get 0. But the math that we did was very good, the math that we did was sound, and it's important to understand all the principles that go into solving limit problems. We're going to do just one more. You'll see problems like this quite often when dealing with the limit-trig combos. Let's go ahead and plug in 0, and we get sine of 0 over sine of 0, which gives us 0 over 0. It's indeterminate, and we're dealing with the limit-trig combo. The interesting part with this problem is there's a sign on the top and the bottom. The limit property that we know is the limit as x goes to 0 of sine x over x, which equals 1. So let's see what we can do with this. The easiest way to attack this problem is to separate the top and bottom of the limit. So we have the limit as x goes to 0 of sine 8x over 1 times 1 over sine 2x. Then if we multiply the first term by 8x over 8x, that will give us the limit as x goes to 0 of 8x sine 8x over 8x. And you can see the limit property right there. Let's do the same with the second term. If we multiply the second term by 2x over 2x, that'll give us 2x over 2x sine 2x. And you can see the limit property right there. So now if we rearrange what we have the limit as x goes to 0 of 8x over 2x times sine 8x over 8x times 2x over sine 2x. I still have my limit properties, but I've moved the 8x and the 2x together. Now my x's cancel each other out. 8 over 2 can pull out of the limit and reduce at the same time, and then each of my limit properties just equal 1. So now what I have is 4 times 1, which just equals 4. There's a restriction that x can't be 0, and there's a removable discontinuity at 0, 4. And before we're done, let's come back to this problem one more time. Pretend this had been sine squared 8x over sine squared 2x. What would be different then? Well, we would just have two of the same thing. We would have sine 8x over 1 times sine 8x over 1 times 1 over sine 2x times 1 over sine 2x. We would do this entire process. Again, we'd multiply this one again by 8x over 8x. We'd multiply this one by 2x over 2x. And then as we move forward, we would just rearrange with more terms than we had before. But the principle stays the same. So whether these problems were squared or cubed or to the 5th power, any power, we would be able to just separate out each of the sine terms on the top and bottom and then multiply by a fancy version of 1 to make the arguments equal to the other variable term. Does that make sense? All right, guys. Good job. If you have any questions, be sure to let me know. Hang in there. Have a great day.